Log on, tune in, find out. Another good idea from Cambridge.
Who, along with Margaret, is also on the advisory board for this program. Simon.
Thank you very much, Phil, and thanks also for the invitation to give this talk. Phil asked me to speak about biomedical imaging, which was a little bit daunting because it's a pretty big topic. I qualified the title just this morning as inverse problems because it's an inverse problems meeting, and it helps narrow down one or two of the topics. I'd like to say in advance that it's a fairly personal view, and I apologize in advance if I'm leaving out anything that people regard as critical. I'll be talking very little about my own work, mostly about largely about work done in the Centre for Medical Image Computing and elsewhere. So I'll acknowledge people at the end, but I'll also try and do that as I'm going. And again, apologies in advance if I inadvertently leave anyone out. I decided to to try and break it down into a few topics. So originally we were talking about biomedical imaging, so I think of imaging as direct or indirect. So direct imaging is what happens when you take a photograph with an old-fashioned camera or a digital camera. You simply acquire data, and the data is what you work with. You don't do any further processing of it. And that plays a role in biomedical imaging, just as it does in computer vision or machine vision. And then there are other technologies which are also just acquiring data, but not so straightforwardly as simply with cameras, but they're still, you might call them direct, because they're just looking at the data as it's acquired. By indirect imaging, I mean the solution of an inverse problem. The measurements that you take are not what you want to analyze, so you put it through an inverse problem step. And then we can look, more or less the whole of the electromagnetic spectrum has been exploited, and in addition we include acoustics with ultrasound primarily. And then when we start thinking about inverse problems, we start discussing the posedness, whether some problems, if the data is acquired in the requisite format, are pretty well posed. Generally speaking, a working definition of well-posed versus ill-posed is if the decay of the spectrum is polynomial versus exponential. A lot of the models in tomography involve a transport equation, which we'll study, and then a lot of interesting classification, or an interesting topic, is how that equation behaves across scale. I'll also look at some what I would call image analysis problems. So a large part of medical image processing consists of either taking sort of data from a direct imaging modality or from a indirect modality, assuming that it's being reconstructed to the best possible standard, and then looking at further steps such as segmentation or classification. And those kinds of problems are quite similar to what you have to do in machine vision. Then I'll look a little bit at multiscale, and the last topic I'll look at how some of these things kind of interact with each other, and the interesting topic of hybrid imaging. Okay, so if you look across scale, we can look at a number of different modalities. X-rays are obviously operating primarily at quite low scale, but in fact X-rays can come, depending on their energy, at wavelengths across most of the spectrum. Ultrasound tends to operate in wavelengths of a few millimeters or a few centimeters. When you look at very small scale structure, we can do it with electron microscopy. I won't discuss that today. What's called positron emission tomography, I'll talk in more detail about what these mean if you're not familiar. Usually has a resolution towards the poorer end of the spectrum, so it's having a resolution of a few millimeters or centimeters. MRI is a very popular modality. It has very good resolution. And optics plays a role across all different scales. It's not straightforwardly used in medical imaging, but it's used quite extensively in biological imaging. Just look at the basic optical imaging system of a microscope. We'll see that the main criterion for resolution is the diffraction limit. So the basic idea of a microscope is that you just have two lenses. We have a lens which focuses at infinity down to the focal plane, and then it's brought back out from that focal plane to the image plane with another lens, and the magnification is just the ratio of the focal lengths of the two lenses. There are some interesting things that you can do in microscopy by interfering in the Fourier plane. This is where dark field microscopy lives and Schlieren microscopy lives. But again, I won't be talking a lot about that for the sake of time, only because that's not really too much to do with inverse problems. So you can play with the magnification by simply varying these focal lengths, but it doesn't help you get better resolution. And the reason is that the resolution is diffraction limited. And the essential criterion is simply called the numerical aperture, which is the ratio of the diameter of the aperture to the focal length. So we just define the numerical aperture as the sine of this angle, and the transverse resolution is proportional to that. You can define the resolution limit by the point spirit function with the famous Rayleigh criteria. So we just look at the image of an impulse at one point in the image plane, in the object plane, sorry. We look at it in another point in the object plane, and the Rayleigh criterion is simply essentially saying that the separation, if you treat the point spirit function as a Gaussian decay, the separation should be at the size of the full width half maximum. So if it were a Gaussian, this would give us about 0.61 lambda over numerical aperture. Well, people have tried to beat the diffraction limit with just optics. So one of the most successful things is the confocal scanning laser microscope. And this is takes a different idea. What we have is now an active element, which is the laser. The laser is going through one lens system. Through this is a kind of halfway mirror, which allows reflection here, but also transmission. It refocuses into the object plane, and then we can control by various means of moving the laser. For example, we can control the point at which we refocus that, and then we scan through this image plane, and we just observe the object plane, and we re-observe it with a second lens system. So the idea is that it gives us 3D imaging, it gives us no out of focus background, it gives increased contrast. And it's quite easy to see why you get a better resolution, because the laser is simply being refocused to a spot, and then you're imaging that spot directly. So now the PSF is simply the directly imaging in the image plane, not through this first lens system. And if you look at the types of points spread function we get from a wide field microscope versus a confocal microscope, you get a much sharper resolution. But in fact, at the end of the day, you get about a √2 improvement in transverse resolution. That's not the main point. The main point is to get the depth resolution. So here you see image of a biological specimen with a wide field microscope, where you're getting blurring due to the in-depth integration over depth versus this depth resolution that you get from the confocal. So the confocal is giving you a 3D image by scanning. that's purely done, that's a purely direct imaging technique, in the sense that we're not doing any reprocessing or inversion of this data, we're just looking at that data. Of course, this data may be then put through any number of post-processing techniques to segment, classify, count, estimate parameters. So now let's look at what we mean by indirect imaging. So there are four widely used clinical methods for medical imaging. Well, one is X-ray CT. So X-ray CT is very well established, invented, researched in the 60s and started to become into clinical practice in the 80s. And now every hospital will have them. Primarily looks at hard tissue, and it's widely used, for example, of looking at trauma due to particularly head injuries due to accidents, looking for micro cracks in the bones. But the way it works should be familiar to many people. Have an X-ray source, a radiating patient, and an array of detectors. This is all rotated round. If you look at an individual projection, this is also very familiar. This is what's called a radiograph, and of course this has been known for much longer, and this is just an example of looking at the data. So in this case, the data itself can tell you some things, but it consists of integrals along the line going through the body, and that assumption is based on assuming that the propagation of the X-rays are not deviated by scattering, for example. So there's just straight lines. And we have a very nice analysis of it. We say that if f is the function we're looking for, s hat is the direction of the ray. Then we form a little local coordinate system perpendicular and along that ray. Then the attenuation of the light is given by the negative exponential of this integral. So if we take the measured intensity of X-rays over the input intensity of X-rays, take its negative log, we have a simple linear integral, which is called the radon transform. It's just a transformation from a function in the two-dimensional space here into another function, which is parameterized by the angle. So if we stick to 2D, it's just one parameter, the angle, and the lateral distance perpendicular to the ray. And the famous inversion formula comes in many varieties, but was known even by Radon in 1917 when he's studying stars, trying to analyze the interior stars from the radiation received, and it has this elegant form. There are several other different versions of it. So this is an indirect imaging, but it's relatively well posed, provided that we have what's called complete data. And complete data means essentially all the angles. So we can think of that, we only need half of them because of the time we get around the other side, the data coming back along the beam is the same as the data coming down the beam. But if we have this complete data, this formula is exact, and the posedness of the problem is only polynomially badly posed, which is very good news. Emission tomography looks similar. There's different ways of doing emission tomography. The principal ones are PET and SPECT. There are some differences between them which I probably don't have time to exactly discuss, but here's positron emission tomography I decided to look at because it looks more like CT. Now we have a molecule, so we have an active contrast agent that's biologically bound to things of interest physiologically, as opposed to just looking at anatomy. The contrast can be embedded into metabolically interesting molecules like glucose, so you can look for its uptake. You have a positron emitting isotope on one of those atoms. As that emits, it goes a very short distance before being annihilated by an electron, and then emitting two gamma rays, which go almost in a straight line, modulo conservation of energy. There is a very small uncertainty about the origin of this due to the uncertainty about the decay or the survival length of the positron before it's destroyed by the electron. That doesn't occur in SPECT. SPECT is just spontaneous emission instead of a positron of gamma rays, but we don't have this problem, but we have other problems because we don't get this simultaneous acquisition. The nice thing about positron emission is that every time you get an event here, you get an event here, so it helps us sort out where the photons are coming from. But from our mathematical point of view, so there are certain things that govern the resolution, principally the nature of the collimator that you use in the detector. If you very narrowly collimate, you can get better resolution, but you have many less photons. You're throwing away photons. If you widen that out, we get a better signal, but we get worse resolution. So there's a trade-off there. But we also have the fact that the photons they're higher energy than X-rays, but they still might be attenuated and they might be scattered. So the photons that come here are not simply the line integral, but there's some small loss. So this is represented in this version of the forward problem. It looks quite similar, that we have an activity integrated on line, but it's also attenuated by loss due to attenuation and scattering. Well, again, there are many versions of the inversion of this. There's an explicit inversion formula for this problem too. But when we're dealing with low photon counts, we can also start to look at it in terms of a statistical viewpoint. And because it's a Poisson process, the number of photons arriving at each detector, it can be posed in terms of what's called maximum likelihood expectation maximization, which takes the form of an iterative algorithm, which looks like this. So here we have the measured data. We have an estimate of the image. We put it through this mapping, take the ratio, and the R star is the simple back projection, the adjoint of the integral operator here, which essentially means just back projecting along the same lines that we used here. And it's normalized by the back projection of a constant. When we'll talk about regularization, we'll see that this can become strongly ill-posed, so we have to put regularization to that. But this is the basic formula. If we had arbitrarily precise data, we can iterate this formula, and it will converge to a fixed point. MRI is also widely known. This involves a large magnetic field used to induce alignment of the nuclear spins of the molecule of interest, and almost all magnetic imaging, at least in the clinic, is done in terms of just the proton, so the hydrogen atom. Although there are versions of it based on other molecules like fluorine and sodium and phosphorus, but they're much slower and much more complex reconstructions. Basically, the idea is that you, in practice, what is done is you have a 3D thing to reconstruct. We do, first of all, a slice selection, which means that we apply a radio frequency pulse which lines up the nuclei in a certain slice. You frequency encode by a gradient field, and you phase encode by pulse selection. So the frequency encoding and the phase encoding give you 2 degrees of freedom in a plane, which can map to a complex variable, and it turns out quite nicely to be simply the Fourier transform. So the way it works is we have this slice selection profile which lines the nuclei up. They start to dephase over time. There are of course there are quite a large number, and it's quite subtle how the pulse sequences are used to image. This is just one, which is called spin echo. We put another pulse which gives 180 degree flipping of those orientated spins, and then you wait the same amount of time until they rephase. And then to a very good working model, the data that you acquire is just the Fourier transform of the parameter you're interested in the plane. So the simplest way to think of MRI is simply to acquire the data, evenly sampled in K-space, and apply just a simple FFT to it. Now, that's standard way of doing things, but things become more interesting when we want to do things faster, and so we might want to sample with different strategies in case space. We can't no longer use a Fourier transform to invert, and we have to use more powerful image inverse problem methods to offset the undersampling in case space. I'll try to come to that later. And the last one is ultrasound. Ultrasound simply consists of an array of transducers sending a wave into the body, and then in its simplest form simply looking at the time of arrival. So it's just travel time of the pulse in the direction and back. And again, the normal, so this should really perhaps be under direct imaging, because the simplest way to look at ultrasound is simply to look at the map of the travel time. And here you get a lot of effects due to speckle. You also have, to some extent, variable sound speed, but variable sound speed is much less of a problem in ultrasound than it is in geophysics, for example. Nevertheless, with bones, have a speed of maybe twice what they do in soft tissue. So there can be some distortion due to that. But a lot of post-processing can go on, and recently one gets these kind of very nice-looking 3D renderings of the fetus in the womb. But there's also a version of tomography, version of ultrasound which corresponds to tomography, which one example is shown here, where you have an array of sources, ultrasound sources and transducer detectors in transmission mode and rotated around the subject. So here we're seeing true inversion, and now we don't use simply the same radon transform we used before, because the waves in K space are not going along straight lines. So, but nevertheless, we can you can make equivalent back projection type reconstructions of this, and we can get reconstructions again mainly of amplitude, but sound speed as well. And then there are issues to do with non-uniqueness of getting, for example, attenuation and sound speed. This is just an MRI, a comparison showing presence of some cysts in a breast. Okay, so what about ill-posed imaging problems? Well, the first thing I mentioned was that when we do CT, we're assuming full angle. But what happens if we don't have full angle? Okay. This is one example from medical imaging called tomosynthesis, but undersample X-rays or limited angle X-ray occurs in many other areas, and there'll be some, Bill, for example, will talk about some other problems in this related to security. I think that's today. But in what's called digital process tomosynthesis, as opposed to what we showed with the ultrasound scanning device, one assumes we don't have limited angle because the access to the breast is limited by the chest wall. So only limited angles occur, and when one does that, you get quite good resolution in the transverse plane, but very bad resolution in the longitudinal direction. And what established theory tells you that you can detect edges in this kind of data if they are parallel to direction of propagation of rays. So if you only had one X-ray projection, of course, you could see anything whose edges were in the same direction, but you wouldn't be able to discriminate between a structure whose edges were perpendicular to the ray. When you have limited angle, you get a slight ability to discriminate, but it's usually quite bad. So here you see in 3D the effect of this limited angle gives you this bad distortion. What we see here is a 3D image of a breast. This is another image taken at a later time where it's been distorted by movement. This is the reconstruction if we take each of those data and reconstruct them separately. And here we combine the reconstruction with a registration step. So what you see is some improvement in the longitudinal resolution. A problem that's widely been researched by inverse problems community is electrical impedance tomography, where we use low frequency electromagnetic radiation. So let me just low frequency electromagnetic radiation is used in a small number of electrodes. So here's a sort of benchtop system where you have a small number of source electrodes and measurement electrodes. And then the inverse problem consists of finding the coefficients of a second order PDE of the voltage, which depends on the conductivity. So this kind of approach is done. We have to use a forward model of the forward problem based on, for example, finite elements, and then do some nonlinear optimization to get this 3D map. But here we're getting this image of a rat brain, and we're looking at spreading depression reconstructed in 3D. You get very poor resolution, but the attraction of these modalities is that you're getting a contrast which you can't get any other way. So it's a sad fact of life that often the highest resolution comes with the poorest contrast. And so this is why people are quite excited by applying these things together, either in what's known as multimodality or as what's known as coupled physics. And I'll come to that at the end. This is optical tomography, which operates in a similar way. This time we use light, but as opposed to using direct imaging and assuming no scattering, we're going exactly the opposite and assuming very high degree of scattering. So we actually solve it with a PDE-based method quite similar to impedance tomography, but based on the absorption rather than the conductivity. But the physics of the problem looks quite similar. We have arrays of fibers delivering light and receiving light. We build a finite element model, try to match this model to the data, and we get this kind of reconstruction. In this case, this is from UCL. This is a system in the neonatal intensive care unit, and this is a baby who had intraventricular hemorrhage, which is revealed here by this bright spots in the ultrasound. This is just as a validation step, and here you see it as this increased absorption. So again, we're getting low contrast, but we're getting low resolution, but we're getting a contrast that we don't see any other way. This can also be done in a functional way. This is now a normal baby being stimulated with having its arm pulled. That stimulates the motor cortex, and we can use, in this case, a boundary element method to model the change in the predictive measurements due to changes limited to the cortex. And here we see this reconstruction where the activity corresponds to the motor cortex in the neonatal brain. That's similar to what goes on in EEG imaging. So EEG, MEG are methods which look directly at the electrical or magnetic fields due to spontaneous activity in the brain. So that's no longer probing the fields, but just looking at the spontaneous emission with activity. So again here we have a very ill-posed, in fact non-unique problem. Similar methods are used with boundary element methods, for example, to do the forward mapping, but strong use of priors is usually required to restrict the limits of the solution. And this is quite highly, extensively used in neuroimaging studies. So we're getting away somewhat from classical imaging here, because we know what we're doing, some kind of mapping where we're simply trying to project the activity onto a stylized map of the cortex. It's not meant to be anatomically realistic, it's just a topologically equivalent representation of the activity. And then the question of solving more complex analyses in terms of state equations of some X is some neural state or some abstract representation of the brain connectivity, U is the voltage, theta are the parameters of the experiment. Let's get back to imaging, and let's look again at this transport equation. So when we looked at the radon transform, we presented it in this form as line integrals, but if we now look at it as a PDE or as a differential operator, it takes this form. It's simply given by the one-dimensional rate of change along a line of a field U plus attenuation along the line goes to 0. So this operator T, parameterized by mu A, has an inverse, which is this line integral. And that's what led to the ray transform. That's in the absence of scattering. In the presence of scattering, we have this more complex form here. Now, the attenuation is due not just to absorption, but to absorption and scattering. And we also have this term which rescatters photons back into the direction of propagation with a local operator S. Now, there's many ways. This is extensively studied. It's quite a difficult equation to study mathematically, but it has a very simple physical intuition to it because it just relates to photons propagating and being rescattered, because the scattering operator is not continuous but only at points. So one way to look at this is to formally write it as a Neumann series, and it takes this form here. If we take this T inverse is the ray transform, it's just the integral along lines, then in the absence of any scattering we just have the standard solution, and then we can look at successive approximations which consist of rays that are propagated until they are scattered at a point and then repropagated from that point. And the interesting thing in medical imaging is that the number of terms that you need depends wildly on the problem that you're addressing. So in basically speaking, the higher the energy, the less terms you're going to need. In nuclear medicine, PET and SPECT, the presence of these secondary scattering terms is measurable, but it's really just a nuisance. It's on the order of 10-20% perhaps of the signal, and there are some mechanisms we can physically discriminate against it. You can discriminate against it spectrally because they lose energy, and you can do some simple processing in the acquired projection domain akin to something similar to what's done in the deblurring problem. When you get to lower energy, the presence of this terms becomes all pervading. There's a slight way you can rewrite it that's convenient. If we simply take the first solution, T inverse applied to Q, and call it a source, or call the application of the scattering to that, we call that the uncollided source, rescattered once, then we can get a solution in terms of what's called the collided flux, which when added to the uncollided flux gives you the full solution. So if we look here, these are some models just by solving the transport equation using finite elements. As we increase the scattering, we have very weak scattering. The ray is essentially just propagating almost in a straight line but being attenuated. As we increase the scattering, we start to broaden out the density in the off-line direction. As the scattering increases, you see this uncollided part is still present, but the collided part is becoming more and more dominant. So this leads to what is sometimes called mesoscopic imaging, which is looking at samples which are larger than just at a scale which is larger than just the scattering length between scattering events, but smaller than what occurs in this diffuse optical problem when we abandon this transport model and just regard everything as essentially a kind of random walk. So some attention is growing on this for imaging biological processes, for essentially sometimes thought of as 3D microscopy, looking at the interior of living organisms without needing to use high energy. So there are a couple of different ways. One of them is called optical projection tomography, and this works exactly like CT. You simply have a source collimated via lenses and detected with an ordinary camera. We acquire the projections through it, and they look exactly like an X-ray sinogram, and just standard filter back projection results in this 3D reconstruction. So this has become increasingly used as a biological tool. This, by the way, is an alternative version of the inverse radon transform known as the filtered back projection formula, which consists of Fourier transforming, projecting into Fourier space, and weighting with a filter which increases with frequency. But this gives us this complete exact optical analog of X-ray CT. But there is an actual problem with this, which you don't see explicitly said here, it requires index matching between the support of this object and the imaging system. In other words, so the specimen has to be embedded in some fluid with high refractive index so that attenuation and refraction are negated. But that fluid essentially doesn't support living things. So we can't look at living things with this mechanism. But the images that you get are very, very striking. Then there is an alternative to this called light sheet microscopy, which uses a cylindrical lens and refocuses into a line. Again, does rotation and tomographic reconstruction. It's known as SPIM, and it gives you this higher resolution, isotropic resolution, but it still needs a kind of matching liquid to see it. So there's a challenge to try to do this in the presence of scattering. So here is some things that we worked on this with optical projection tomography including scatter. Now what we want to assume is that there isn't a matching refractive index. The refractive index matching, by the way, is the same mechanism that H.G. Wells proposed for making the Invisible Man. That was how he saw it. The Invisible Man was taking a drug which changed his refractive index to that of air. The OPT is embedding the object in a high resolution liquid, a high refractive index liquid of the same refractive index as the tissue, but essentially making it invisible so that the only contrast is due to either just absorption or fluorescence. But if we take that problem away, we can now look at this, but now let's look at what happens if we measure not just the light that's being propagated directly through the object in transmission, but also some that's scattered at an angle. So here you see a simulation. Now we have a structure which has some absorbing and some scattering quantities present in it. And this is the direct transmission. What you see now is that the absorption and the scattering essentially just is creating shadows that you simply see that can't distinguish between the two. Whereas the off axis is only looking at the scattered data. Well, the reconstruction I don't really have time to explain the details of how that works, but it's an optimization based method. Create a forward model and iteratively reconstruct. And we're able to separate out the absorption scattering. Here, in fact, that's just recast as the attenuation coefficient. That's the sum of absorption and scattering, and the albedo, which is the ratio of the absorption to the transport coefficient. So we're able to separate that. And the reason is because we take off-axis measurements. So we're getting two sets of measurements at each angle, not just the transmission measurement, but also the scattered at an angle. I think we use 45 degrees here. Okay, let me now turn to a slightly different topic, which is some of the aspects of post-processing. So then, as I mentioned, if you take the images as a given, then you may want to do post-processing tasks to them. So one of the commonest is segmentation or classification, labeling of different objects into their types. But another is registration, because increasingly the interest becomes in multimodality imaging. We're assuming that data is taken with two different modalities. The patient has to be moved between them, and during that movement, their internal coordinate system can't be completely consistent. So I just want to go through this one bit because it's going to tie up with some of the actual work on multimodality and hybrid imaging as well. So let's see how this is posed. The idea is to find a mapping between an image XA and an image XB, where we're assuming that there is some correspondence between the two. In other words, we're assuming that we can find a vector field that takes every point in one image into another. Now, there are some qualifications that have to be applied, which again I'm not going to go into. I noticed that there are some talks on this in this week, so we may hear more about this. But there are some qualifications for it. For example, assume that the correspondence is exact, that there's no structure in one image that's not present in another, or that, for example, if these were taken at different times, that they're not that something hasn't been created or something destroyed. That's a different problem. One of the first things that you have to do is you have to assume that the images are overlapping and that we're only looking at optimizing over the intersection of the domains of image 1 and image 2. And then there are quite a lot of different strategies applied. There's what's called, well, first of all, we can do it either in 2D or 3D, or to some sense we might want to do it between the two, because you might have a slice, for example, ultrasound sometimes gives you a slice at an arbitrary orientation, and you want to register to that to a 3D data obtained, for example, with MRI. So all of these things are considered in these problems. But the main thing that mathematically we distinguish between rigid rotation, rigid transformation, which means that we're just considering rotation and translation, maybe with scaling due to the internal coordinates of the system, or maybe skew as well, but these are all affine problems, or between non-rigid transformations, which means that the transformation we say is a vector field, and we project it into some basis, such as polynomial functions, spline functions, or we could even use physically based models. And that's another common approach, is to assume something based on what we think the physics might have happened to transform it. So one problem that's commonly addressed is looking at the difference between a patient lying down in a scanner, such as a CT or an MRI, and standing up, which might occur with EEG, or, for example, in mammography, which is usually done in compression of the patient standing up, versus lying with the breast hanging prone. So then the difference between the coordinate system can, to some extent, be predicted by physical deformation. So it can build physical models based on biomechanics to limit the space in which the deformation is described. And then there's some things that you have to consider is what are you being optimized? What are you optimizing? So if you're optimizing, if it's the same modality taken to 2 times, you can optimize a least squares difference, so just an L2 difference. But more commonly, we have to assume that the images are taken in different, with different imaging contrast. So we look for some measure that's independent of those imaging parameters. And one is the correlation coefficient. But more predominant, I would say, these days is to look at what are called information theoretic measures. So here we see an MR and a CT of the same patient. If you look at them and we plot each pixel as a pair on a graph, and we look at the joint histogram of their occurrence, what you might expect to see is that if something like bone had a correspondence, if you were exactly lined up, then although we don't know what the mapping is between bone and MR, we could say that all of the bone and all of the has one intensity value, and all the all the MR bone has one, and all the CT bone has another. So that when we plot it, they will have a peak in the histogram at that point. But if they're misaligned, that peak will get spread out. So what you see is, if you plot these things, you see this peakiness and also this kind of dispersion. And this dispersion you think of as this representing this misalignment. So in qualitative terms, the goal that you're trying to do is to transform this image, or this one, let's say this one is being transformed, so that the histogram has as much peakiness as possible. And we just simply measure that with entropic measures. This one is PET MR. They see the same thing. That when it's registered, it has this beta alignment. Maybe it's not completely clear here, actually. But anyway, the idea is that you modify the transformation so that it makes this histogram as sharply peaked as possible. So the way that that's thought of is in terms of this information theoretic measure. Joint entropy, which is just the integral over that density function times its log. It's just a simple definition of joint entropy. Or another one that's thought to be slightly more optimal is what's called mutual information, which is the sum of the marginal entropies minus the joint entropy. Now there's some subtlety about which of these is optimal, which I won't have time to go into, but I want to mention it here because it has some impact on multimodality reconstruction as well. Because what we can do is, rather than just treat registration by this entropic optimization, we can also treat joint reconstruction in the same way. So let me, I think I'm getting a little bit behind time, so let me skip forward a little bit. This is just showing one version using B-spline representation for the deformation field, and you do it in a hierarchical way. We have a control point spacing of 20 millimeters, 15, 10, and here we see this is just diffusion contrast enhanced MR mammography. This is now this is simply serial investigations of the same breast volume, but because in between the scans the coordinate system is not consistent, we see this and subtract them, we see quite a lot of noise. If they're registered and subtracted, you see now the presence of this tumor is much more apparent. You can see it here, but it's distorted by this misregistration information. Okay, let me now get to a couple more things. So I want to say something about higher order imaging multi-scale. So this is, again, something that's come up in the last 10 years or so, is to ask what more structure you can investigate. So if you look at, as I mentioned, the principal molecule being observed in MR is the proton, and the principal presence of the proton is in water. So largely MR is just looking at the density of water. That's why bones show up almost black in MR, and different structures in the brain show up more. So grey matter in the brain has more tissue, whereas the white matter is the part that has all the fibers. It's kind of the wiring that's connecting up all the different parts of the brain, so it has a less contrast in it. But anyway, what we can ask is, what is the possibility, if we think of water propagating in random walk, does it propagate isotropically, or does it propagate along directions, or does it propagate in more complex ways? Well, it turns out that the same mechanism that was used for the conventional MRI can be adapted a bit. And what we did before was we put this slice selection pulse and then this inversion pulse. Now, what they do in something called pulse gradient spin echo is that they put now another gradient in between the slice selection and the inversion. And what this has the effect of is that it causes the spins to their phase to change in the direction of this gradient. Then when the inversion comes, it doesn't completely invert everything. So beforehand, the inversion reversed this and we lined up back here. But now we line up with some direction which indicates the alignment with the phase of the system. And the way it works out is that you have this Q is this direction in which you apply this gradient pulse here, and that we can acquire essentially a function as we can acquire a phase as a function of this direction, and we have complete control of this direction modulo the amount of time it takes, which can be lengthy. But essentially what is thought of here is that you're acquiring now at every point in the image a Fourier transform. There's a normalization which complicates things, but essentially we're getting a Fourier transform on a sphere of a function. And if we analyze that, we can start to ask more interesting questions about how that relates to the underlying model. So this is mainly work lent to me by Danny Alexander. So what's being sought after in these brain connectivity is this orientation of fibers locally, so that we can start at one point in the brain and track our way to another point in the brain. And the problem comes in when we have crossing fibers. We have on a gross level just a kind of a mixed direction tensor. So if we simply add together fibers orientated here and orientated here and look at them at a macroscopic level, we can't tell the difference between, or let's say we took 3 in 3 different directions, we couldn't tell the difference between that and an isotropic direction. So what's called diffusion spectrum imaging is essentially outputting what's called the orientation diffusion function, which is a probability measure of the directionality of the fiber orientation. Now let me show you how it looks. So this is 2 examples. This is what's called diffusion tensor imaging, which has been around about 10 years, which assumes that the orientation is simply described by an ellipse. So that, in other words, the all that's being sought are the directions and the eigenvalues of a 3x3. Oops, sorry, it's on some sort of timer. 3x3 matrix. Whereas with diffusion spectrum imaging, you're getting at each point actually a functional sphere. Now here it's being decomposed into spherical harmonics. So we see that in some places it's almost isotropic, some places it's got one direction of orientation, and some places it has mixed orientation, indicating crossing. So the game here is to think of at a lower scale what's called a fiber orientation distribution function, a probabilistic measure of orientation of fibers, and then to try to predict how this is the forward model, to predict the diffuse orientation distribution function. And then they want to infer by model selection between the two. So using this leads to this topic called tractography, which is now asking us to, given a point in the image, to follow the fibers. So we may have situations like this where we don't know whether we should be following this way or following this way. So the name of the studies here is to improve the ability, and this is all done in probabilistic frameworks. So they're all done including MCMC techniques to marginalize over the uncertainty, to give us this orientation. This is really highly sought after by neuroimaging scientists, to look at, to really be able to map the connectivity from one part of the brain to the other. I think I'll skip. This is just showing how you can, given some particular DODF, you might, for example, think of it this way or think of it this way, and how do we discriminate between them? And the way it's being adopted by Danny Alexander's group is to look at this microscale models, the fiber orientation diffusion function, and to use model selection methods to probabilistically estimate the difference between the two choices. Okay, so I think I've got 1 or 2 minutes, so I'll just try and quickly finish this. So let's look at multimodality and hybrid very quickly. And then let's just mention, because we didn't mention it before, the probabilistic framework, the Bayesian framework. So in the simplest thing we were looking at before, we were looking at just models which we would call likelihood. So those people that work on Bayesian methods will know that we define a joint PDF as the sum, or as the product of a prior density and a likelihood density to form the posterior. And if we simplify things into a normal distributions, then we say that the posterior is just the product of a Gaussian likelihood, this is this term, and a Gaussian prior. And if we maximize that, we minimize the negative log, it looks like what's conventionally called regularization, which means that the data fitting term, which is the negative log of this, and a penalty term, which is something which Bayesians would call the prior probability density of the image. Well, how does it look? If you use what's called a smoothing prior, isotropically applied to an image, it means that if we just look at the increasing probability density, or the increasing probability, it's trying to enforce images which are smooth to a greater extent, but isotropically smooth over the whole image. some of you may know about this total variation method, which says that the smoothing induced by the prior should not destroy edges. So it's something which sometimes it's an example of what's called edge enhancing flow. It's used very commonly in image processing, which says that the density, prior density, is smooth but allows to include jumps due to the indication by the data of the presence of edges. But we can do more than that. If suppose we have multimodality and we say that there is some indication of edges from another problem, that's to say we enforce smoothing over within regions imposed by a secondary modality but not across the boundaries of it, we can get this kind of result, which tends to enforce piecewise constant solutions. And finally, we can look at combination of TV and prior edge distribution, which allows to enforce edges due to a prior, but also edges that are coming from the data itself. This is what's called the diffusivity function. It's just the local weighting. It represents the anisotropy of the smoother. So how does that impact into imaging? Well, if we did deblurring, we take an image, we blur it and add noise. This is a classic ill-posed inverse problem. We can try to deconvolve it with the total variation prior, or if we have this exact knowledge of edges, we can get a very good result. But this is maybe slightly cheating because we know where the edges are before we deblur it. If we apply the same thing to in-painting, that means we have missing data here. So now the isotropic prior tries to just isotropically blur in the regions without any knowledge of the edges. But if we have the knowledge of the edges, we can blur within the regions and fill in this missing gaps. If we apply that in limited angle tomography, as we saw in the digital tomosynthesis problem, the presence of limited angle leads to this poor reconstruction of edges which are parallel to the beam. So here the limited angle is in this direction. We get good reconstruction here, but poor here. And here this is now a prior, and we can fill in this image by imposing this prior density in the places where the data is missing. And finally, in the CT, in the SPECT reconstruction, we do SPECT with noise, with a limited set of angles. We get a poor reconstruction, but again, if we impose the edges, we can get almost perfect reconstruction. Let's mention this information theoretic. So information theoretic says that we want to maximize the peakiness of the histogram between the two images. We use that as a constraint. We see this in MR PET now. If we look at the reconstruction, we just reconstruct and look at the histogram with MR, we see this poor definition of the classes. If we use this constraint that they should be isolated, we get this much better reconstruction. Okay, let me skip ahead and just talk about coupled physics. This is ultrasound. This is photoacoustic inversion. That means that you put in a light pulse and we generate ultrasound. And we do a well-posed reconstruction using time reversal. And we get very high resolution 3D images, but they're not quantitative. If we put in a model based on diffusion equation, we can get good reconstruction absorption, but poor reconstruction scatter. If we use a better model for the light propagation, we can get this improved reconstruction. Okay, so I should stop now. Some topics I didn't mention, compressed sensing, and I didn't really say much about dynamic imaging or multispectral or microwave, which Margaret mentioned. Now let me just finish there and say, maybe in the rest of the week we'll discuss some of these comparisons. It was just a partial list that I put up. I think I've overstayed my time, so I'll stop there. Thank you.
Thank you very much. That was a remarkable tour. And, I think given the time, we should move directly on to the first half-hour talk. But I'm sure Simon would be happy to begin the discussion of the week during tea. Thank you.